What's good, everybody? Today, this is intro to chem video, and whether you're new to chemistry or just trying to study for the final exam, well, this is a pretty good video to start with. So, let's get into it. Matter is the stuff of the universe. So, think about your iPad or your iPhone or a folder. Anything that has mass and volume is called matter. Is part of matter. And chemistry is the study of matter and its properties, the changes that undergoes, and the energy associated with these changes. And by studying matter, we can kind of understand the unique properties that matter has. So a property is kind of like a trait or characteristic that gives each substance its unique identity. And there's two types of properties. There's called a physical property and there's a chemical property. So if you were to, let's say, find a rock, for example, some physical properties of the rock would be the mass of the rock, the color of the rock, the size, the temperature. Is it malleable? So is it ductile? What's the texture of the rock? So these are just characteristics of a substance by itself, so you're not changing or interacting with another substance. Chemical properties, these are characteristics of a substance that involves changing or interacting with another substance. So you're changing the composition of that substance. One example, well, think about paper or wood. Paper and wood catches on fire really easily, and how flammable something is a chemical property, or how reactive something is. That's also another chemical property. You probably heard about the states of matter before: solid, liquid, and gas. Let's take a look at them. So, solids, they have a fixed shape and definite volume. They are non-compressible, and solids can be hard, they can be soft, they can be flexible, and on a molecular level, solids vibrate in place, and the molecules, they have strong attractive forces. Liquids have a fixed volume, but they don't have a definite shape, and liquids cannot be compressed to extent like solids. On a molecular level, the molecules slip past one another, and attractions are constantly being broken and formed. Gases have no fixed shape or volume. Gases are compressible, and they don't have like a surface like solids and liquids. On a molecular level, the gas particles are far away from each other, and there's no attraction between them. Now, let's talk about change in matter. Matter can be changed in one of two ways. So there can be a physical change. Let's say if you were to break a pencil in half, well, that would be a physical change because you're just changing how the pencil looks. You're not changing the pencil into like another substance, you're not changing the chemical composition. Chemical change, however, you are changing the composition. So, in a physical change, you don't form a new substance. You don't really need as much energy as chemical changes. There are changes in the physical properties, and the mass of substance, there is no change in that. And its physical changes, they're also reversible. But chemical changes, you do form a new substance, and you need more. The quantity of energy needed is more. You change the chemical properties and chemical composition. And also, it's very difficult for you to reverse a chemical change. So, if something were to react with something and create a new compound, let's say, it's very difficult to go back to where you started. Now, you've probably heard of what an atom is before. Building blocks of matter. Yes. And how does an atom look like? Well, an atom has neutrons and protons in the nucleus. So neutrons are these neutrons are neutral, and these protons, they're positively charged. And they're orbited by these electrons. And if you go on the periodic table, you might have noticed that, well, let me just pull up my periodic table right now. You can see how there's these big numbers on each of the elements. And why are these numbers here? Well, each element is unique because each element has a different amount of protons. That's one thing that's unique about them. So, for example, an atom of hydrogen is going to be different from an atom of helium because helium atoms, they always have two protons, but hydrogen atoms, they only have one. So it doesn't matter how many electrons or neutrons a hydrogen atom has, because it's never going to be the same as helium atom, because it's never going to have more than one proton. Then it's going to be another element, and it's not hydrogen anymore. Matter can be classified into three types based on its composition. So you have elements. So, the elements on the periodic table, those are part of pure substances. And compounds. Think about water, H2O. Water is also a pure substance. Why are they pure substances though? Well, they're pure substances because their composition is fixed. So, and they can only be separated by chemical means. So, for example, if you have a molecule of water, pure water, it's always going to be 2 parts hydrogen and 1 part oxygen. And if you were to increase the amount of hydrogens or increase the amount of oxygens, it's not water anymore. So the composition is always fixed. What about mixtures? Well, 2 characteristics of mixture. What makes a mixture is that their composition varies. That's one. And 2 is that they're physically mixed together. You see how compounds, H2O, they're chemically combined together, but mixtures, they're physically combined together. So in a mixture, you can still separate the elements or the stuff inside the mixture. Now, there are 2 types of mixtures: heterogeneous mixture and homogeneous mixture. So, heterogeneous mixture, well, take a look at sand or oil and water. Heterogeneous mixture is just when you see one or more boundaries between the components in a mixture. So, for example, if you see oil and water together, you can see 2 layers. But homogeneous mixture, you can only see 1 layer. And homogeneous mixtures, they're also called solutions. So, in a homogeneous mixture, because it has no visible boundaries between the components, the particles are evenly distributed. So, just to recap, mixtures are different than compounds because the proportions of the components can vary. If I were to open up a lemonade stand, and let's say there's another dude, my friend, has a lemonade stand, well, my lemonade can have more sugar than his lemonade. So the proportions of the components in lemonade, they can be different from each other. In addition, the components can be separated by physical means. So my lemonade can be separated by physical means, not chemical means. Because lemonade, well, everything's physically combined. It's not like one compound. So I'm just gonna do some practice problems right now. So You tell me if this is either a compound, a homogeneous mixture, or a heterogeneous mixture. Well, pure water, well, that's just going to be a compound because, well, its structure is fixed. It's chemically combined together and its structure is fixed. What about tap water? Tap water is a homogeneous mixture because one, what makes it a mixture is that there's all these different components that they're physically combined together. And two, what makes it homogeneous is that, well, you can only see one layer in tap water. So, and finally, what about rice pudding? Well, if you search up rice pudding on Google, like, it's pretty good. I recommend y'all trying it. But rice pudding is a heterogeneous mixture. Why? Well, because you can see there's two. You can kind of see like the rice grains, and you can see like the liquid that it's in. So you can see two distinct layers. That's a heterogeneous mixture, and also because the components can vary. Now we are going to go back to the periodic table, and we're just going to learn some other concepts, other trends in the periodic table. So, a group in a periodic table is a vertical column in the periodic table. So, group 1 would be, you see the H, the element 1, the H, that stands for hydrogen. Element 3, lithium, the Li, that stands for lithium. 11, which is sodium, Na, and so on. You can see the vertical column. And group 2, that would be Be, element 4, beryllium, Mg, element 12, magnesium, and so on. Now, these groups, right, they all have their unique properties. The first group is called the alkaline metals. These types of metals are very reactive. They're kind of like a soft, white, shiny kind of metal. And the next group, group 2, so the second vertical column, the one I was talking about, beryllium, magnesium, that column is called the alkaline earth metals. Alkaline earth metals, for now, just know that they're a bit less reactive than the group 1 elements, but they're still pretty reactive compared to some of the other elements. Now, this big group you see here right now, we're not going to worry about that for now, but they're called the transition metals. But we're actually going to go all the way to the end of the groups. So we are going to go to group 18. So group 18, they are called the noble gases. And for now, just know that noble gases are very stable, so they don't react that much. Now, the group the group to the left of the noble gases, these are called the halogens. And halogens, they are also very reactive. So, one thing to know about groups is that, well, the group number it's in kind of determines the amount of valence electrons it has. So, if you don't know what a valence electron is, let me just show you a diagram real quick. Okay, you might have seen this diagram before. This diagram is called the Bohr model of the atom. And you can see there's kind of like multiple like layers, kind of like, an onion, An onion has multiple layers. This is kind of like an onion. And there are multiple like energy levels, we call it, or shells that an electrons can go to. And A valence electron is just an electron on the outermost energy level, the furthest energy level away from the nucleus. Now, what I mean by the group number determines the amount of valence electron, we'll look at group 1. So let me go to my periodic table real quick. So, group 1 elements, they only have one valence electron. So, they're going to have one electron on the outermost shell. Group 2 elements, beryllium, magnesium, calcium. So these elements are going to have two valence electrons. Now we're going to skip the transition metals for now. And we're going to go to group 13. Now, group 13 elements, they're going to have three valence electrons. So you can kind of ignore like you can kind of ignore like the 1 in front of the 3. So just ignore that. The number after the 1 is the amount of valence electrons it has in these main group elements, as we call them. So the main group elements are just kind of like the elements without the transition metals. We're only focusing on those elements. Next, we have group 14. So we're going to ignore the 1 in front of the 14, and that's how many valence electrons it has. It has 4 valence electrons. And you can kind of see the trend here. So group 15, that's going to have 5 valence electrons. Group 16, these ones, they're going to have 6 valence electrons. Group 17, 7 valence electrons. And finally, group 18, 8 valence electrons. Now, the reason why noble gases are so stable is because noble gases, they have 8 electrons on the outermost shell, besides helium. But helium is also really stable, but we're not going to focus on that for now. We're not going to focus on subshells or anything, but just know that 8 electrons on the outermost shell make an atom really stable, which is why elements all the way to the left, so the alkaline metals I was talking about, and the halogens, group 17, those elements are really reactive because, well, the alkaline the alkaline metals, they really want to lose that electron to get a full valence shell. And the elements to the right, they really want to gain an electron. So, an atom of, let me use this example. So let's say we have a sodium atom of Na. It has one valence electron. So it would be really easy for that atom to just lose one electron and get to the noble gas, so the 8 electrons on the outside, rather than having to gain 7 electrons. And this is the same thing for fluorine, so the symbol F, as you can see. That element, it really wants to gain electrons because it's a lot easier to just gain 1 electron and get to the 8 electrons on the outside, on the outermost shell, than having to lose all of its valence electrons. And this is kind of the introduction to our bonding unit we're going to be talking about. So, the first type of bond we're going to talk about is called an ionic bond. So, think about it like this. One atom really wants to gain electrons. One atom really wants to lose electrons. So they make kind of like the trade offer. I give you electrons, so you get your full valence shell, and I lose my electrons, and I get a full valence shell as well. So that's pretty much the concept of ionic bonding. Take an example. So table salt, NaCl. Table salt, the Na atom, it has one valence electron, and the Cl atom has 7 valence electrons. So the Na is going to give the chlorine atom, the Cl atom, one of its valence electrons. And boom, you can see what's happened. Both of these atoms now have a full valence shell. And the reason why they are attracted to each other, well, think about it like this. Our atom is neutral, okay? So it has the same number of protons as it does with electrons, okay? So an Na atom has 11 protons and 11 electrons. What happens when an Na atom loses its electron? Oh, it turns into a positive ion. So when you lose an electron, you're losing a negative charge. And now the atom has a +1 charge. What about the chlorine atom? And so a chlorine atom has 17 electrons and 17 protons. But what happens if it gains an electron? Well, electrons are negatively charged. So this atom of chlorine is going to be a negatively charged ion. So remember this. If it's a positive ion, it's called a cation. Cations are positive. And if it's a negatively charged ion, these are called anions. Anions, negatively charged ions. And what happens? What happens when this negatively charged ion meets this positively charged cation? Well, guess what? What do you know about opposite charges? We have a positive and a negative charge, and we know that opposites attract. So this is going to become a NaCl atom, aka table cell. I mean NaCl compound. I'm sorry, NaCl compound. Let's take a look at another kind of compound, another ionic compound. We have magnesium, and this has 2 valence electrons. And we have sulfur, symbol S. Sulfur has 6 valence electrons. Now, sulfur wants to gain 2 electrons, magnesium wants to lose 2 electrons. They make a trade offer. So, magnesium gives 2 electrons to sulfur. Sulfur gains the 2 electrons. Magnesium becomes positively charged. Sulfur becomes negatively charged. And boom, they're attracted to each other. And we're not going to worry about naming ionic compounds for now, but this is called magnesium sulfide. And as you can see, well, let me go back to my periodic table. So you can see how elements in the first group, right? They tend to form a +1 ion. And this is because they have 1 valence electron and they want to give it away. The second group, they tend to form +2 ions because they have 2 electrons and they want to give it away as well. You can see group 17, these elements, they form a -1 ion because they're gaining 1 electron. Group 16 elements, they want to gain 2 electrons, which is why they're going to form a -2 charge, a -2 ion, as you can see. And if you're wondering about noble gases, well, they don't really form a charge. As we said before, they're really stable, and they don't really react with other elements. The charges that these elements form, they're usually the same in a group. So you can see if you pull up like a periodic table from Google, you can see there's these like tiny little numbers on like the top right of the element, and this shows the charges of the ions that it forms. And down a group, the charges of an ion, they're usually the same. So group 1 elements, most of them, I mean all of them actually, they're going to form a +1 ion. So elements in the same group, they share kind of the same ion that they're going to form. We have to travel back 2,000 years to the early Greeks to kind of learn about how the history of the atom developed. So there was this guy called Aristotle, and he believed that things like earth, fire, water, and air could be divided endlessly into smaller parts, and those parts would still have the qualities of the original element. But Democritus believed that atoms were kind of like the smallest indivisible building blocks, and he called this atomos, meaning indivisible, which is where the word atom actually comes from. And it wasn't until the early 1800s when a guy named John Dalton kind of made his own theories and disapproved of Aristotle's theories. So John Dalton believed that each element is composed of extremely small and indivisible particles called atoms. All atoms of the same element are identical, and atoms of one element are different from atoms of another element. Atoms of one element cannot be changed into atoms of another element by chemical reaction, and you can't create or destroy atoms in chemical reactions. And compounds are formed when atoms of more than one element combine, and a given compound always has the same relative number and kinds of atoms. And this was a pretty impressive theory for its time, considering that nobody really knew much about the atom. So, as you can see, only the first theory was kind of incorrect, because now we know that atoms are made up of electrons, protons, neutrons. But this was still really impressive, because number 2, number 3, and number 4, they're still correct. And he created a model of the atom, what he thought to be what an atom looked like, in 1803. And he called this a solid sphere model, and just looked like one singular sphere. Nothing much to it. Very different from our model today. Let's go to the late 1800s. So J.J. Thomson, he discovers the electron. But how did he do it though? Well, he had this nearly evacuated glass tube. So kind of all the air was kind of sucked out of it. And it was filled. It had these two kind of electric metal electrodes that were sealed. So the first electrode was the cathode, which was negatively charged, and the anode, which was positively charged. And how this kind of worked was you kind of turn on the power source. In this case, this is the high voltage, and it emits this invisible ray. And the anode's kind of like the thing that guides the particles that come out of the cathode. And what happens is, even though this ray is invisible, when it hits this fluorescent screen, it emits a light. So the screen kind of emits a light that tells you like where the particle is hitting. Now, when J.J. Thomson did this experiment, he placed 2 electric plates in the tube. So one was positive and one was negative. And what he saw was that, well, the cathode ray went to the positive side. And this meant that the particles were negatively charged, because, well, we know that opposites attract. And the only way for something to attract a positive is when you have a negative charge. So he tried this again, but this time he placed a magnet near the tube. And the reason why he placed the magnet was because, well, when a magnet is kind of applied to this moving particle that has a charge, well, it's going to bend. And that's exactly what happens. So when he placed the magnet near the tube, the rays were reflected by the magnet. And this means that they also have, once again, it has charged particles. So, final thing he did was, well, he changed the material of the cathode. So, a cathode, wow. So, he changed the metal of the cathode to another metal. And what he discovered was that the results were the same, which meant that all atoms have this charge. So not only did this one type of metal have this negative charge, but also another type of metal had this charge. And what really was going on here was this cathode was kind of releasing electrons. It was emitting electrons, and it was being kind of pulled towards this positive side. And this is when in 1904, this is when J.J. Thomson, he created his model of the atom, and he called this the plum pudding model. So there were these negative electron plums scattered around this positive pudding, or you can think of this as a chocolate chip cookie model. But it wasn't long until another person created his own model of the atom. And his experiment, well, it's called the gold foil experiment, and it's by none other than Ernest Rutherford. Now, he was actually a student of J.J. Thomson, and he wanted to investigate the structure of matter based off of J.J. Thomson's model. And it was known at the time that if everyday matter was electrically neutral, the atom that makes the matter up must also be neutral. So what he did was he had this sort of lead container, and it emitted these alpha particles. Now, for now, just think of alpha particles as these positively charged. They're positively charged and they're pretty big. And these particles, they were confined to this narrow beam. So they were shooting out in this narrow beam. And there was this gold foil that was supposed to be like bombarded by these alpha particles. And the particles, wherever they landed, they were detected by a zinc sulfide screen. Now, what Rutherford had expected was, well, because the plum pudding model, like the charge of the electrons was like dispersed evenly throughout this atom. So his kind of prediction was that, well, the alpha particles would just pass through the gold foil. Nothing really happens. Wrong. Well, although like a lot of the alpha particles pass through the gold foil with not much deflection, there were some alpha particles that had major deflections. And Ernest Rutherford was very surprised by this. And what he concluded was that the charge inside of atom, it must be condensed into this, well, today we call it the nucleus, right? And how did he conclude this? Well, we know that opposites, we know that same charges attract each other. And only if an atom had this really condensed positive charge would the positively charged alpha particles kind of deflect from the positively charged nucleus. So he actually he stated that, well, first of all, this indicates that the probability of actually hitting this charge, it was a very low chance. And why? Because it was like a 1 in 2,000 alpha particles that actually bounced straight back. And what does this indicate about the size of whatever has been hit compared to the size of the gold foil in the atoms? And what he concluded was that alpha particles were smaller than the gold atoms. And Considering the facts that alpha particles are positively charged, well, once again, this meant that the charge of whatever deflected them must be positive. And based on the evidence and understanding, well, he composed of this model called the nuclear model. And it's still probably really popular. It's still used really popular throughout today. But it has this really dense nucleus with a positive charge. And it has these smaller electrons. It's kind of orbiting this nucleus. And he also concluded that the atom was made of mostly empty space because, well, there was a really low chance of actually hitting anything. Now we have the Bohr planetary model. So this was made in 1913 by a young Danish scientist, and his name was Niels Bohr. So, as you can see, this atom, well, the nucleus is pretty much the same. We can see that there's like these orbits around these like nucleus, and these are like where electrons can occupy. So, this first orbit or first shell is called n equals 1. This is the first shell. This is the shell closest to the nucleus. And electrons, they can move up and down these shells. So say that there's electron in shell 2. If an electron gains energy, it can go to shell 3. If electron loses energy, it goes back to shell 1 and emits the energy as light. So basically, the reason why there are all these different colors is because, well, you can see that there are electrons that go from a higher energy state to a lower energy state. And it's like these combinations of these electrons going to high to low energy states that kind of make up the light we see today. For example, electron going from, let's say, the third energy level back to the first energy level is going to produce a different light than an electron going from the second energy level back to the first energy level. Now, when an electron gains energy, it can't go in between these orbits. So you can't go to like the 1.5 shell. There's no such thing. You can't go in between. When an electron gains energy, it becomes unstable because it wants to be close to the nucleus. The nucleus is positively charged and the electrons are negatively charged, so it's attracted to the nucleus, which is why it can't really stay in this high energy state for long. Now, just one extra thing to add, the the required energy to go from the first energy level to the second energy level is greater than the amount of energy it takes from the second energy level to go to the third energy level. And that jump is less than going from the third energy level to the fourth energy level. And you can kind of see the pattern. So as you go on, you need less and less energy to go to the next energy level. Now, the last model is kind of crazy. So, it was made by a guy named Erwin Schrödinger in 1926. And he believed that, actually, he stated that the electrons do not move in like set paths. So, like, it's not like the Niels Bohr model where it was like these set orbits that electrons were supposed to kind of follow. It was actually impossible to know the exact location of an electron. And well, instead there's just these clouds of probability. So like these clouds of probability that you'll find an electron. So as you can see in the model, the greatest density of, the greatest chance that you'll find an electron is near the nucleus. And as you get further away from the nucleus, the chances are less and less. Now we are going to dive into precision versus accuracy. Say that you're a person who loves to play basketball. Go into a basketball hoop, playing with your friends, and or one day you're just practicing on your jump shot, shoot a couple of times, and you see that you bricked all your shots. All your shots hit the backboard. Now, what does this mean? Well, if you want your shots to be accurate, you have to shoot the ball through the hoop. That's what makes it accurate. But your shots are not accurate. So this is an example of like a result that's not accurate. So, in measurements, if we're measuring like how far away your shot was away from the hoop, you know, your shot would not be accurate. But because you consistently hit the same spot on the backboard, you consistently brick, this means that your results are precise. So precision is just basically how consistent your results are. So you would say something like say just Stephen Curry. He's really precise at shooting threes. He's precise and accurate because he's consistent with his 3 pointers, and he's really accurate as he makes a lot of the 3 pointers. We have 3 students who measure 20.0 milliliters of water in the tube and then weighs the water in the cylinder on a balance. Each student measures 3 times. So we want to find out who has high accuracy and who has high precision. So let's take a look at it. For our first person, Johnny, his first trial is 20.1, second trial is 20.2, 20, and then his average is 20.1. Now, as you can see, Johnny's results in his trials are very consistent. So Johnny has a high precision. Is he accurate though? Well, kind of our starting measurement, if you were to get like a perfect measurement, that would be 20, because that's the measurement we start with. So in this context, 20, the average of 20 would be kind of like the perfect score. And in this case, Johnny has an average of 20.1. And this means that Johnny has high accuracy because his result is very close to the actual result. So Johnny has high precision and high accuracy. Jeff measures 200 milliliters of water. Second trial 200.4. Third trial 200.2. And his average is 200.2. Now, immediately you can see that his results are pretty consistent. Even though his result is extremely wrong, I don't even know how you get 200. If your result is wrong, but it's a consistent wrong result, that's still precise. So it doesn't matter if you have a consistent amount of good results or bad results. Either way, it's precise. But we definitely can't say he's accurate because, well, our kind of perfect measurement would be 20 and he's way off. So Jeff is only precise. Now, Bob, first trial 20, second trial 30, 10, average is 20 milliliters. And you can see his average is super good. It's very accurate to kind of our expected result. In fact, this is kind of like the perfect result. But you can see how, even though his average might be really accurate, his results aren't accurate. And you can see that first it goes to 20, then 30, then 10. His his kind of range of numbers is very like widespread. So therefore, you can say that Bob has high accuracy, but his precision is very low. So the results are just that Johnny is accurate and precise, Jeff is only precise, so he's not accurate, and Bob is only accurate, but he is not precise. What I am going to do now is talk about a topic called sig digs. So, sig digs are important when you're doing mathematical calculation. For example, like measurements, for example, if you're converting centimeters to meters, something like that. Sig digs are really important because, well, it shows you the amount of sig digs shows you how many digits you need to round to. So, let's get into it. Say we have a number 1, or a number 2, 3, 4, 5, 6, 7, 8, 9. So any number between 1 to 9, any non-zero number. So any non-zero number is a sig dig. So if we were to have a number like 192, there would be 3 sig digs. Why? Because all of these are non-zero numbers. And another thing to know is that any sandwiched zero are significant. So say that we have a number like 10,098. 10,098. Well, we know that these non-zero digits are significant. But if there's zeros between these two numbers, kind of like squished in between them, these are also significant. So if I have this long string of zeros, and just have this 1 9, all of this would be significant. Now, let's say we have a number like 230. Well, any non-sandwich zeros aren't significant. Unless, well, there's 2 exceptions. But if it's just a number like this, there's no decimal here, this 0 is not going to be significant. But if we were to put a decimal here, the 0 becomes significant. So without decimal, 2 significant digits. With decimal, 3 significant digits. What if we are dealing with decimals? Let me just get a couple numbers, and first of all, remember that any non-zero digit is a sig dig, and any sandwiched zeros are significant. So automatically, we know that these digits are significant. But now what? Which one of these parts of zeros are significant? Well, any trailing zeros in a decimal are significant, which means that if we were to have a number like this, everything from the 1 all the way to the last 0, this is going to be significant. Doesn't matter how many zeros we put, all of this is still significant. Doesn't matter if we put 1, 2, 3, so on. Any trailing zeros are significant. We have a number like 19.00. Yes, there's no like number here that's not non-zero, but remember, any trailing zeros in a decimal are significant, so there would be 4 sig digs in this number. Now what I want you to do is, I want you to determine how many sig digs that these numbers have. So, first one, we have, let's say, 34,000. Second one, so we have just 34. Third one, let's see, we have 500. Okay. 500.0, 30 point, just a dot, 0 point. Okay, so let's get into it. For the first example, well, automatically we know that the 34 is significant. So we already have 2 sigdigs acquired. But the rest of the zeros, well, you don't see a decimal here, right? And they're not kind of sandwiched in between another non-zero digit. If there was like a 1 here, for example, all of these zeros would be significant. But since there's no 1 here, there's only 2 sigdigs. So why does it put a decimal there? 2 sigdigs. Next one, 34. Well, just from the last example, any non-zero digit is a sigdig, so this would also be sigdigs. 500. Once again, 5 is significant, but these zeros, they don't really have a decimal, or they don't have like a 1 or 2, 3, any non-zero behind it. So this is just only one sigdig. 500.0. See, there is a 0 here. So now this whole thing is significant. Why? Well, we know that any non-zero number is a sigdig. If there's a decimal here, we know that any kind of sandwiched zeros are also sigdigs. And we know that any trailing zeros in a decimal are significant. So this whole thing is significant. This would be 4 sigdigs. 30 point. No point, 1 sigdig. A point, this 0 counts, and there is 2 sigdigs. Finally, 0.40900. Wow. Remember that these things, anything sandwiched in between them, any zeros sandwiched in between these non-zero digits are sigdigs. So we have 3, and any trailing zeros are significant. So this would be 5 sigdigs. Now, how would you actually use, or how would you actually find the amount of sigdigs when you're doing multiplication, addition, subtraction, division? How would you actually do that? Say we have something like 1.2 times 3. Okay. Now, when we multiply this, we're going to get 3.6. Okay, 3.6. But what we need to do is we need to look at the amount of sigdigs in each of our numbers. This has 2 sigdigs, and this has 1 sigdig. And when you're multiplying numbers and you want to round to the correct number of sigdigs, you have to round to the number that has the least amount of sigdigs. So in this case, because this number has the least amount of sigdigs, we're going to round to 1 digit. So our 3.6, well, we're going to round to this digit. So we take a look at our digit here. If this is greater than 5, we round up. Less than 5, we round down. So this is greater than 5. So our final answer is going to be 4. Okay. Say we have something like 2.45 times 3.6. If you put this in your calculator, you're going to get 8.82. 8.82. 8.82. Now remember, you have to round to the number with the least amount of sig digs. In this case, 3.6 has the least amount, and this has 2 sig digs, compared to this, which has 3 sig digs. So what we're going to do is we're going to only focus kind of on these two numbers. We look at the number after the second digit. This is a 2. So in this case, because this is less than 5, we are going to round down. So our final answer is going to be 8.8. So multiplication, division, you're only going to have to round, or round your answer to like this number with the least amount of sig dig. What about addition and subtraction? 3.6 plus 2.45. In addition problems or subtraction problems, I like to write the numbers in this way. When I do the calculation, 5 goes down here. 0, 1. You're going to get 6.05. Now, the rule for adding and subtracting is that, well, all the numbers that have like the least amount of decimal places, you have to round to the number with the least amount of decimal places. So in this case, because this has the least amount of decimal places, we can kind of draw a line to the extra kind of numbers. And in this case, because this number is a 5, we round up. So this is our final answer is going to be 6.1. So if number has less amounts of decimal places than the other number, in this case 3.6 has the least amount of decimal places, well, the extra decimal places from this number, well, you're kind of going to ignore that. You draw a line from like the decimal places these two numbers share, and then like the rest you can kind of ignore except for the rounding part. So let's do another addition problem. So 3.675 minus 2.12. Let's do it this way. We line up our digits and we kind of draw a line to the extra digit, because, well, this number has the least amount of decimal places. So we draw a line from like kind of the point where this number has like no more decimal places. So there's going to be a 5 here, 9 here, 7 here, a dot, and a 5. And since, well, this number is a 5, we round up. So our final answer is going to be 5.8. Now, kind of don't get confused with like multiplication, like the rule for multiplication, division for sig digs, and the addition subtraction sig digs. Because multiplication sig digs tells you how many sig digs you need to round to, but like the addition subtraction doesn't really tell you how many sig digs you round to. See how like you can have this super long decimal? Yeah, you can have something like 1.2 0.756 subtracted by like 2.157, and in this case you're going to get 4 sig digs if you were to solve this equation. So addition and subtraction, it doesn't really tell you how many sig digs you round to. It just tells you like which decimal places, you can kind of ignore, but it doesn't tell you like the specific amount of sig digs you need to round to. While in multiplication and division, if you do like a multiplication like 3.4 times 5, you only have to round to this 1 sig dig. Doesn't matter if there's a decimal. Now, what happens if we have mixed operations? So, kind of a combination of multiplication, division, addition, subtraction. Let's do a problem. 4 plus order of operations matters. So you're going to do this part first. 6.5 times 5. If I enter this in my calculator, I'm going to get 32.5. I'm going to get 32.5. 32.5. A strategy you should do is, well, this only has 1 sig dig, right? And this has 2 sig digs. So in your final answer, you're going to want to round to 1 sig dig. So what I like to do is I draw kind of an underline to indicate that, oh, this is the number I'm really focusing on. So these other numbers, like, you don't really need to worry about them until like the rounding one. You don't need to worry about like the 2 when you're rounding. But other than that, like the other digits, they don't really kind of matter. So you're only going to round until the n when you're doing mixed operations, because you want your answer to be as accurate as possible. So I'm going to do 32.5 plus 3.4, and we're going to get 35.9. Now remember this kind of underline I made on a 3? We have to round to 1 sig dig. So in this case, we look at this digit. It's 5, so we're going to round up. Our answer is going to be 40. Let's do another example. It's 6.5 times 3.47 times 2. First, do the stuff inside the parentheses, because order of operations. So I'm going to have to add up these things. 799. Now remember, this number 6.5 has the least amount of decimal places. So we're only kind of caring about these 2 numbers. So I'm just gonna make an underline there to kind of show that, well, this 7 isn't really significant. So we're gonna get 9.97 times 2, and this is going to equal 19.94. Now, when you're multiplying, well, once again, so I'm just going to make an underline from here to kind of show. Sorry, that was a bad underline. Sorry. I'm just going to make an underline from here to show that these are the digits we care about from this part. But now, because we're multiplying, we have to follow kind of the rules of multiplying. And this only has 1 sig dig, and this really only has 2 sig digs because we're adding. So we have to round to 1 sig dig. So our answer, well, this is a 1. Take a look at the next digit. This is a 19. So our answer is going to be 20. One more. 3.4 times subdivided by 2 plus 3. Do the division first. And 3.4 divided by 2. This is going to be 1.7. This is going to be 1.7. Now this 2 has the least amount of sig digs. It only has 1 compared to 3.4, which has 2. So you're only really going to be focusing on this digit. This digit is kind of the only digit that's significant. We're going to add 3 to this. Since this has no decimal places, since plus 3, since this one has no decimal places, well, once again, we have to follow the addition rule. So we kind of have to cut this 7 off. So once again, from our multiplication, well, we have to round to 1 sig dig. So our answer, look at the 7 here, and we're going to get 5 because we round up. Let's put what we learned about sig digs into use. So say that we got person A, and this guy wants to go to person B, and they are 7 inches apart. So how long would this distance be in centimeters? So you want to convert inches into centimeters. How would you do this? Well, you have your inches here, right? This is going to be 7 inches. And you want to multiply this by our conversion factor. So what we're trying to convert to. This is kind of the crucial step. Always make sure that you place the measurement that you want to convert from, so kind of our original unit, which is inches, at the bottom. And you want to place the measurement that you want to convert to at the top. So remember that at the bottom, this is kind of your original kind of unit, what you want to convert from. And at the top is what you want to convert to. And there was going to be 2.54 centimeters in 1 inch. Multiply this, and you see how when we put the inches and the centimeters in such a way where the centimeters are at the top and the inches are at the bottom, you see how the inches will cancel out. And you're just going to be left with centimeters, which is exactly what we want. 7 times 2.54 is going to be 17.8. 17.8 centimeters. But you're not done yet. We're going to go back to our original measurement. And let's see how many sigdigs there are in our original number. Our original number is 7. This has 1 sigdig. So when you're kind of rounding it to the correct number of sigdigs, always look at your original measurement. Never kind of look at this conversion factor. Just ignore the conversion factor. Focus on the amount of sigdigs in your first, kind of your original measurement. Since this has 1 sigdig, we're only going to be focusing on this number. The digit after this number is a 7, so we're going to round up. Our final answer is going to be 20 centimeters. See how the number of sigdigs in 20 matches the number of sigdigs in 7? And also, sorry about that. And also, our units have been converted. So always make sure that kind of when you're checking your answer, those steps have been done. And also, kind of another mistake people make is that they just write 20 as your answer. This is not correct, because this could be 20 yards. This could be 20 meters, So always make sure to put your unit after your answer. Say that we have 3.5 feet. And we want to convert this to yards. 3.5 feet goes first. And we're going to multiply this by, once again, our conversion factor. What goes on the top and what goes on the bottom? Well, remember, the unit we're converting from goes in the denominator, or the bottom. The unit we're converting to goes on the top, which is yards. There are 1 yard in 3 feet. So when you multiply this, the feet cancels out. Let me get my calculator real quick. And we are going to get 1.16, and then the 6 is just repeating. 1.16 yards. Remember, sigdigs. How many sigdigs does 3.5 have? Our original kind of measurement. This has 2 sigdigs. This has 2 sigdigs. So we're going to round our answer to 2 sigdigs. We're only going to be focusing on these terms. So let's see the third kind of digit in this. The third digit is greater than 5. So we are going to round up. Our final answer is going to be 1.2 because we rounded up yards. How many inches are there in 6.51 miles? So I'm sorry I wrote it this way, but we're trying to get from miles to inches. So how will we do this? Let's set up a plan. Because miles to inches is kind of a confusing conversion. So I'm just going to do like kind of a mini map. I want to convert my miles into feet. So a easier kind of conversion. And then I want to convert the feet into inches. Because converting miles directly to inches is kind of annoying. So I'm just going to use units, kind of easier conversions, easier step by step. So let's get 6.51 miles, okay? And we want to convert it to feet. So our miles is going to go on the bottom because this is the unit we're converting from. And the unit we're trying to convert to is feet. So this goes on top. And there is 5,280 feet in 1 mile. Now we're not done yet. So like the miles cancels out, but we want to convert the feet into inches as well. So we have to create another conversion factor. So how many, well, remember that the feet goes on bottom. Because now we got rid of the miles, but we need to get rid of the feet and go to inches, which is what we're converting to. There are 12 inches in 1 feet. So the feet will cancel out. Enter this into your calculator. Times 5,080 times 12. And we're going to get 4. We're going to get this pretty big answer, 0.6. And you could write this in scientific notation if you want, after we convert it into the correct number of sigdigs. This has 3 sigdigs. So this is kind of all I'm caring about, these 3 units. Let's take a look at the next unit. This is less than 5. So 4 is less than 5. Which means that we round down. So our final answer is just going to be this. And then just 1, 2, 3. If you want, you can convert this into scientific notation. I'm just going to keep it like this. So this is going to be in inches, and our final answer is this, in inches. And you see how we successfully converted miles into inches, and we successfully rounded to the same number of sigdigs as this. So how do we actually write like an atom? How do we actually use like specific notation to represent, the properties of certain atoms? So say that, if you have an atom of carbon, and you want to show that carbon has 14 protons, and you also want to show that carbon has 8 neutrons. How would you kind of write this? Well, we kind of use something called A, Z, and then X notation to represent atoms. So the this represents how number of protons and neutrons. So the A represents the amount of protons and neutrons in the atom. We have 14 protons right now. We have 14 protons and 8 neutrons. 14 plus 8 is 22. Therefore, the atomic mass of this specific carbon atom is 22. Now what about the Z? The Z just represents the Z represents the number of protons in the atom, or aka the atomic number. So if you go to the periodic table, all the elements have kind of like a number next to them, kind of like a pretty big number, and that shows the atomic number, or the number of protons. So in this case, number of protons is 14. So you're going to write 14 on the bottom. Finally, the X kind of represents this symbol. So this represents the symbol of the specific element that we're going to talk about. And in this case, our element is carbon. If you look in the periodic table, carbon is element 14, and carbon is the symbol C. So carbon is the symbol C. So this is what an atom of carbon with 14 protons and 8 neutrons looks like. This is how you would represent this. What if, let's say I have an atom of lithium, okay? Lithium. And then I just put a dash, and let's say I put 6, okay? How do you represent this? This problem doesn't represent the number of protons or neutrons it has, so how can I figure this out? If you look in your periodic table, lithium is element 3. So, therefore, the atomic number is 3. Whatever element, an element's on, for example, lithium, if it's on element 3, it has 3 protons. An atom of hydrogen, that's element 1, so the H. And hydrogen atoms, they only have 1 proton. Therefore, they're element 1. So you see how the atomic number of these elements kind of corresponds to the amount of protons they have. So you don't need to remember like the specific amount of like protons for every atom because you got your periodic table for that. So lithium 6, this has 3 protons. But now what? If you ever see something written like this, in this way, this represents the atomic mass. This represents kind of how heavy the atom is. And because the atomic mass is 6, and there are only 3 protons, well, let's just refresh. What is the atomic mass? Well, that's right. This is the number of neutrons and protons. So if we already have the number of protons, which is 3, let's find out how many neutrons there are. The atomic mass, we subtract that from the amount of protons so that we get to the amount of neutrons. In this case, there's going to be 3 neutrons. So this is just a way, if you're ever asked a problem where you have to find out how many neutrons are in an atom of like an element in this specific type of like notation, now you know that this is the atomic mass subtracted by the atomic number. This is not really part of our notation, but might as well throw it in there because this can be really useful sometimes. So if we're trying to find out the number of neutrons in an atom, well, this is just going to be the total atomic mass, and this is subtracted by our atomic number or number of protons in the atom. But anyways, back to our thing. So we know the atomic mass, and we know that when we're writing in AZX notation, right, the A represents the atomic mass. And since the 6 represents the atomic mass, it goes on top where the A is. Finally, we have our symbol. Well, this X right here, this will represent Li. or lithium. If you go to your periodic table, like Li might look something like this, and then there's like 3 on top. So you're gonna put Li here. This is the symbol for lithium, and there's your answer. So let's talk about allotropes and isotopes. So when you're young, have you ever played with like a toy block, or you were building something, and you had like these blocks, okay? And you use these blocks to make, let's say, a tower. Have y'all ever played with like dominoes before? Yeah, that's pretty fun. With dominoes, you might even have, I don't know, maybe with like certain types of blocks, you might have built like a bridge before, or any other kind of structure. So you use these toy blocks, and in return, there's all these like different structures that you can build. Well, this is kind of the same for elements. And like a certain element, let's say this is an atom, okay? Well, if you have like a group of these atoms, there's so many ways to rearrange these atoms. And when you rearrange these atoms in like certain ways, different rearrangements of the same element are called allotropes. These are called allotropes. So allotropes are just the ability of an element to kind of exist in different structures. So they are the same element, but they exist in different structures. For example, let's take a look at carbon. Allotropes of carbon. This is carbon with a C. Allotropes of carbon include diamond and graphite. If you search up a picture of graphite kind of structure, you can see that graphite kind of looks like a honeycomb. So like kind of like these like hexagon shapes, But diamond, if you search up a picture of diamond, it kind of looks like kind of a cubic kind of structure. So you can see how these two things, because they have different kind of structures, allotropes, because allotropes have different structures, they have different physical properties. So for example, look at like your pencil. Your pencil is made out of graphite. And graphite, if you ever like touched graphite before, kind of in a pencil, that thing's pretty easy to break. You probably broke like, pencil in half. But diamond is very hard. I doubt that, you can actually break that. It's very, very hard. So as you can see, both of these kind of allotropes, they have different physical properties because of the different structures they have. Let's take a look at another type of allotrope. So let's take a look at allotropes of oxygen. So allotropes of oxygen. So this is going to be an oxygen atom. And allotropes of oxygen are O2. This is O2 and O3. One, the ozone. Let me just. Alright. Okay, so one of these allotropes will kill you. This is ozone. Ozone will kill you if you breathe it in. And one gives you life, which is this oxygen gas. So you can kind of see that allotropes, they all have all these like different properties because of the crystal structures. Once again, now let's talk about isotopes. Let's talk about isotopes. You have an element of carbon, right? Now, or let's make this simpler. Let's say you have an atom of hydrogen. This is a hydrogen atom. Hydrogen atom. Now, hydrogen atoms, they always have one proton because, well, they're element 1. But have you ever wondered, like, can the amount of neutrons vary in an atom? And the answer to that is yes. So, an atom of hydrogen, they can have, like, let's say 1 neutron. An atom of hydrogen can have 1 neutron. An atom of hydrogen can have 2 neutrons, and so on. So you can see that, well, these kind of hydrogen atoms, well, they can have different amounts of neutrons. So isotopes, they're basically the same element, kind of different versions of the same element. And for isotopes, we're kind of going into like diving deeper into the amount of neutrons. So as you can see, allotropes are the same element, but with different structures. But isotopes are different versions of the same element. So it's nothing to do with like the different like structures it can make. Now, isotopes, because like, say you can have hydrogen with one neutron, because this is the atomic mass. As we reviewed before, this is going to be the atomic mass. And since we already have 1 proton, that means we should have 1 neutron as well. Now, there can be like something like hydrogen 2, and there can be something like hydrogen 3. And these two like different versions of hydrogen, they also kind of have different properties. So the summary of isotopes is that, well, all of the same element have the same atomic number, but not the same mass number, which means that the amount of neutrons in one element can vary. Imagine that you have a candy jar at home, and it has yellow candies, red candies, and blue candies. So look something like this. Now, what these candies represent is they represent an isotope of an element. So, iso for short. Isotope. So, this represents the isotope, all these candies right here. And you can see there's 3 different isotopes. This is the yellow isotope, red isotope, blue isotope. You can think of it like that. Now, in nature, just like how in the candy jar there are more pink isotopes than both of these isotopes, you see, there are more pink candies than yellow and blue candies. Well, in nature, there can be more of one isotope existing in nature than another isotope existing in nature. And, if you go to your periodic table, let's say we have an atom of potassium. This is going to be symbol K. So, your atomic mass, your atomic number either goes like here or on top, depends on which periodic table you're using. And then it's going to be like 30. The average of the atomic mass of potassium is going to be 39.0 and then something. Well, you might be wondering, how can you calculate this atomic mass if there's 3 isotopes of potassium? So there's going to be potassium, so the question is, if you have these 3 isotopes right here, how can you calculate this atomic mass if all of these 3 isotopes have different atomic masses? How would you calculate this? And the answer is, this is kind of like an average. This is the average atomic mass. And this is kind of I'm just going to teach you how to calculate the atomic mass. So potassium 39. This has an atomic mass of 38.96 in AMUs. So all of these are going to be in AMUs. This has potassium 40 has isotope. What? Potassium 40 has atomic mass of 39.96. And this is going to have atomic mass. Potassium 41 is going to have atomic mass of 40.96. Now, remember when we were talking about the candy jar, how there were like different candies of pink, different amounts of candies of pink than blue and yellow candies? Well, out of all the potassium atoms, so out of 100% of potassium atoms, this is made up mostly of 93%. So out of a total of 100% of these potassium atoms or isotopes, you can see here, 93.26% of it is going to be potassium 39. 0.01% of it is going to be potassium 40, and 6.73% of it is going to be potassium 41. So what you do is, well, let me just zoom in a little bit. You take your abundance, your fractional abundance of isotope 1. So we see how in our first isotope, our percent abundance is going to be the percent thingy, so the 93.26%. And we are going to convert this into like an actual number. So we're going to turn this percent, we're going to get rid of the percent, and what we're going to do is go back 2 units. So this is going to be 0.9326. And you take the fractional abundance of the first isotope and you multiply it by the mass of it. So we're going to multiply it by 38.96. Now you're going to add this to, well, you're just going to do the same steps for all of the other isotopes. So we convert 0.01 to a percent. Well, we want to get rid of the percent. So we go back 2 units. This is going to be 1, this is going to be 2. And we're going to get 0.0001. Multiply this by the atomic mass, which is 39.96. This is a bit messy, but I'm trying to make it work. And finally, this is 6.73%. since we want to get rid of the percent, we go back 2 units. So this is just going to be 0.0673, and you're going to multiply this by, well, the atomic mass, which is 40.96. And if there's more isotopes of this, we keep going. Sorry, what the hell was that? Okay, we keep going until we're done with all the isotopes. Until we ran out of isotopes to, do this stuff on. When we get our answer, so you can use your calculator for this, and if you plug this into your calculator, you're gonna get 39.0947. And you can keep it this way, but no, if you want, you could just round it to 2 digits after the decimal, but anyway, kind of works. And let's check the periodic table. So if you're doing a problem where you have to find the average atomic mass for these 3 isotopes, for like an isotope of an element, well, to check your answer, just look at the periodic table and it'll tell you the atomic mass, the average atomic mass. So if your answer is not close to the average atomic mass, you've done something wrong. And you can see that if I were to go to the atom of potassium, this is going to have the atomic number 19. It's either at the top or the bottom. It depends on which periodic table you're using. And the average atomic mass for this is 39.0983. So, yeah, this is about it. This is this is pretty much it. So you can round it to 2 if you like to kind of match this. You don't really have to worry about sig digs when you're dealing with these isotopes. So remember that when we're doing these problems, this is going to be, we focus on our first isotope and we multiply the fractional abundance of the first isotope by how much it weighs or how heavy it is. And we add that to the fractional abundance of the second one when we add that to the fractional abundance of our second isotope and multiply that by our atomic mass of the second one, and we repeat until we're done with our isotopes. Then we do our calculations and we get our final answer. You can also write this is going to be 39.0947 AMUs. I hope y'all enjoy the video, man. Took me a long time to do this. And yeah, have a great day, guys. I'm sorry that, there's a lot of background noise and stuff.